All right, hello class. Welcome to lecture 8. So, before again, I should make a confession that I recorded this lecture. Unfortunately, the mic was muted the entire time, so I'm here recording it again, which is a little bit frustrating. So if you ever feel frustrated when having to watch these long lectures, feel somewhat gratified that, or perhaps a little bit of schadenfreude, that it's sometimes frustrating for me because in this case I have to go over the whole thing again, which is amusing, but not so much. Anyway, so in lecture 7 we talked about system norms. So this gives us something which we can optimize in our optimal control problem. And remember that, of course, optimal control is an optimization problem. And the system norm then gives us a objective function, right? So for formulating our optimal control problem, we can, actually we should be minimizing. We have a variable, which is our controller. And we now have something to minimize, which is the closed loop system norm of our closed loop system. So it's a function of our plant, which we can't control, it's given, and our controller, which we have some flexibility to choose. And now our norm, our system norm that we defined, can be either the H infinity norm or the H2 norm. So the H infinity norm, if you recall, is actually a norm on the transfer function of the system, right? So if we formulate this as, say, let's call it G hat, right? Then the H infinity norm is the maximum of the magnitude of that transfer function along the imaginary axis over all frequencies, whereas the H2 norm, which is also an option for our system norm, is the integral of the transfer function along the imaginary axis. However, we'll focus for the most part on the H infinity norm because that actually tells us something about the properties of the closed loop system which we're trying to minimize. Specifically, if here's our closed loop system, right? And here I'm going to make this W and Z for continuity. This tells us something about the suppressive properties of this closed loop system from these exogenous inputs to our regulated outputs. And specifically, it allows us to minimize the L2 norm of the output over the L2 norm of the input. So this is useful because what it tells us is for very small inputs, we get very small outputs. Likewise, for moderately sized inputs, we get moderately sized outputs, and for large inputs, well, we get large outputs, but hopefully not too large, right? So it minimizes the effect of these disturbances on regulated outputs. Right. And so in this lecture, we are going to focus on two parts. So the first part of the lecture, which I'm recording again, is formulating a given problem in this framework, right? So to isolate the things that we're trying to minimize, the regulated outputs, as a function of the things which we can't control, the disturbances, the things we're trying to minimize the effect of, which is the disturbances. So isolating these signals and separating them from the things that go to the controller, which are internal to this closed loop system. And so that's what we're going to be focusing. In the first part of the lecture, we'll take some standard representations, the regulator framework, the tracking framework, and formulating it in this closed loop, in this signal representation. And in the second part of the lecture, we'll actually close the loop and figure out what this closed loop system is. So in this first part of the lecture, we'll be focusing on taking our plant, right, and isolating these signals, W and Z, which we want to minimize the effect of, and we want to minimize the effect on, and separating those from some other signals, which are the sensed outputs, so the sensors, which we don't really want to minimize that output, and the actuated inputs. These are things we can control. Right. So that's our goal. In this first slide, we talk a little bit about separating those inputs and outputs, right? And so in particular, we focus on the outputs here, separating our regulated outputs from our sensed outputs. Right? So there's a 2-input, 2-output framework where we want to separate the things we want to minimize the effect of, things we cannot control. Oh, sorry, I'm off the screen. So minimize the effect of, and things we want to minimize the effect on, things we want to be small. And we want to differentiate those from the inputs, which are the things, the actuators, the signals from our actuators, the effect of the actuators on the plant. And the things we can measure. Which are the sensed outputs. Those are things we can generate an electrical signal which represents the things we can create an electrical signal which represents something we can feed back to our controller. So we've got in the closed loop here, we have a controller, and that goes back to our actuator inputs. Right. So let's focus for now on the outputs, right? So what are the outputs of this plant? So there's 2 classes which may or may not coincide in some sense. So the first, of course, is the things that we care about, the things that we want to go to 0. Now this may not necessarily be things we want to regulate per se, right? So for example, in the tracking framework, we don't want our output of the signal to go to 0. We would rather want it to go to the reference input, right? So for example, but the regulated outputs as we formulate them here, right, are the things we want to go to 0. Now, we may not be able to measure these things, right? They don't have to be measurable. They just have to be modelable, right? So we have to be able to find an expression for them. This is in contrast to the sensed outputs, which we may or may not want to go to 0, but the things we can generate a signal for. So for example, maybe you can measure one of the states of the plant, for example, but you don't necessarily want that state to go to 0 because we don't really care about it, right? Maybe we only want a couple things to go to 0. Or maybe that state doesn't actually represent anything useful for us. And so we don't necessarily want to we don't necessarily want to regulate our sensed outputs, although we may, right? So there can be overlap between these two. Between these two signals. But there doesn't need to be, right? They can be entirely separate, or they can be they can have overlap. But in any case, you have to separate them out into separate signals, Z and Y. And so when you figure out what those are, they may be the same thing, right? They may be some duplicates. but we have to actually pull them out and represent them separately into this two-input framework. So they can be overlapped. However, with the constraint, of course, right, that for the sensed outputs, we have to be able to measure them in real time, right? So we have to have real-time measurements of these as an electrical signal. In contrast, on the input side, right, we also want to separate our signals, but there's separation on the input side is a little bit more strict, right? So we separate these into the effect of, right? Right, and these are things we can't control. Right? If we could control them, we would just set them 0 and be done with it. So the exogenous are examples of exogenous inputs are, say, process noise, right? So unmodeled dynamics in the plant. And these may just be our best guess on how they affect the plant, but we have to have some model for the unmodeled dynamics. Other options, right, are the sensor noise. So corruption to our sensor. Obviously, we can't control corruption. If we could, we would just set the corruption to be 0, and we'd be done with it, right? Because who wants corrupt sensor noise, right? So we model sensor noise likewise as an exogenous disturbance. One that's a little bit less obvious, right, is this tracking signal. So the example that I like to think about is the cruise control problem in an automobile, right? So you set the cruise control to be 60 miles per hour, and then you change it to 50 miles per hour or 70 miles per hour or something like that. So you can modify that thing, but the controller doesn't modify that, right? You can't just set that to be 0, right? Because the user has a desired speed, and if your cruise control would always like set your velocity to 0, but it wouldn't be very good cruise control, right? So these tracking signals are things we don't necessarily want. We don't necessarily have a way to, or we don't want to allow the controller to modify, right? And likewise, we don't want them to go to 0 either, but that's another question, right? So these tracking signals, reference inputs, are often what they're called. We want to minimize the effect of those reference inputs on the things that we want to regulate. We'll talk about more the tracking problem in a minute. So as I sort of hinted, right, there's a strict differentiation between disturbances or exogenous inputs and actuator inputs, right? So actuator inputs are the things that we can control. So we have actuators, that's typically how we modify our plant. And they have electrical input signals in a man-made control system. So that our controller can modify those signals as it pleases. Now we'll talk a little bit about limits on that in a later slide. But for now, we assume that we can modify these as we like. Now, unlike the output signals, there can be no overlap between the exogenous inputs and the actuator inputs. Those signals are never the same, right? So okay. So generally, we'll color code these as yellow and color code the outputs as orange. Right. So the first step, right, in analyzing a system to be controlled is identifying all these inputs, right? And then once we've done this, we have a system representation of each of these signals first set of signals is Z and Y, and the second set of signals is W and U. And we give them different letters to allow us to remember that they are in fact different signals. Right. Now, these signals themselves can be vectors, so there can be multiple inputs to each signal. Right. But we concatenate them and separate them in order to avoid misunderstandings. Right. So the next step, right, then is to, once we've identified our signals, is to formulate the feedback control problem, to formulate the optimal control framework by writing an aggregate plant which is different than our nominal plant. So the nominal plant is maybe the system within the system, for example. But this is a larger plant which maps this set of signals to this set of signals. Right. So now one of the advantages, of course, of working in this algebraic framework of linear systems is that once we've formulated this aggregate plant, and we'll talk about how to do that in the next couple slides, we can decompose it into subsystems. Right? Specifically, we can decompose it into individual systems which map W to Z, right? So ones that map W to Z. One which maps U to Z. One which maps W to Y, right? And one which maps U to Y. Right? So 4 different maps, and then we can concatenate these systems together to form this larger aggregate system P. And of course, one of the advantages of working in this algebraic framework is the concatenation, both horizontal and vertical, preserves the structure of the system, right? So the concatenation of systems is a system itself. If we were working with transfer functions, it actually satisfies the same property. So if we had transfer functions for each of these P, we could find the bigger transfer function just by concatenating these sub-transfer functions together. However, that doesn't actually help us that much because, well, there'll be matching poles, and it's unclear what the state space representation is. So notice that this concatenation, however, does not hold for state space systems. So if we have a state space representation of of these subsystems, which we write as A, B, C, D, right? We can't just concatenate these the A, B, C, D together and get a state space representation of this aggregate system. Right? It doesn't work like that because the state space representations are not algebraic, right? You can't treat the state space representations in the same block diagram algebra that you can for the system or the transfer function. One other thing to note before we move on to this next slide is that we write these systems, so our sort of standardized framework for this feedback interconnection works from left to right, right? So left to right. So we write the outputs on the left, and we write the inputs on the right. This is probably a little bit counterintuitive to people who work with block diagrams quite a bit, where we usually write the inputs on the left and the outputs on the right, and we've been doing that throughout the slide so far, or the lecture so far. But the reason we write it in this way is that it makes it easier to write down the equations in this form, which represent the system. So in particular, right, if we write an equation from right to left, right, so the output of the equation goes on the left, and the input of the equation goes on the right. And so we write these this feedback interconnection from left to right just because it makes it easier to write down the equations for the system. Now I get to see if I've forgotten anything. Nope. So that's our goal, right? Our goal is to take an actual control problem in step 1 and write it in this feedback interconnection formulation. Right. So let's take one of, well, 3 sort of common formulations of the control problem and show how this works, right? So we take our control problem, which we write it in this way because this is a way that people generally write this problem. So this is the regulator problem. So we have a nominal plant, P0. And the goal is to design a controller which makes the output of the nominal plant go to 0. So this is in contrast to the tracking problem where we want, like, say, the output of the plant to match a reference signal. So we'll cover that later. This is more the case of, say, a chemical refinery where we have a nominal operating condition and we want to minimize effects of environmental disturbances or temperature fluctuations or unmodeled dynamics on the output of the plant so it stays in sort of that nominal operating configuration. Right? So in this regulator framework, it makes sense that the output of the plant, and here's their output of a plant, the output of the plant is our first regulated output. Because that's the thing we want to go to 0. So let's call that Y1, right? So note that, again, we differentiate sensed outputs from regulated outputs. Because in this model, right, we can't actually measure the output of the plant. We can try and measure it. We have sort of a sensor which attempts to measure the output of the plant. But of course, sensors are never perfect, right? They're disturbed by 60 hertz noise or whatever. And so that sensor measurement is corrupted, or so the output of the plant is corrupted by the sensor noise additively, and that's how we model it, to produce our actual sensed output, Y. Right, so we'll label that as Y. And this is also an output of the plant, right? Because it's something we can measure. But it's not a regulated output. This is a sensed output. And it's different from the regulated output because it has this exogenous disturbance, which is a sensor noise, affecting it. And so we can now isolate an input to the system, a disturbance which we want to minimize the effect of in a closed loop, which is this sensor noise. All right, so let's follow this wiring diagram a little bit further. So we've got the sensed output. Obviously, that's the input to our controller. So there's K. That's going to be down here. Oh, sorry, to be down here. Y, going the other direction. And output from the controller is our actuator signal. Right. So that's the electrical signal that goes to our actuator and somehow affects the dynamics of the plant. Right. So there's this is U, right? And so notice that we branch off U in 2 directions. So I'm going to discuss this first branch first, right? And this is an important point which differentiates the optimal control framework to a great deal from, say, the pole placement problem. And that is that this actuator signal, the strength of the signal sent to the actuator, is also going to be a regulated output. And why do we do that, right? I mean, that looks like an input. Why are we sending it as a regulated output? And the reason is in real control systems, any practical control system, our actuation authority is limited. So this can be due to things like saturation of the actuator signal, or maybe the fact that we just don't want to break our actuator. Remember, actuators have physical interpretations. They're physical mechanisms. And if you send them a really strong input signal, they will either break, they'll break the plant, or they'll saturate and they won't do what you expect them to do. So almost always in the optimal control framework, or in any control framework, you should try and minimize the size of your actuator signal. And so the way we do that in almost every control system that you want to think about is by including the actuator signal, the signal going to the actuator, in our regulated outputs. Right? Now, I guess you could add the process noise to that regulated output, but we don't do that because we can't really have any direct influence on that process noise. So we try and minimize the size of the signal to the actuator. Now, as I indicated, the signal to the actuator can get corrupted. So it may not do, there may be saturation, right? So it may be saturation of the signal. There may be noise in that electrical signal going to the actuator. Or this may just be process noise, some unmodeled dynamics going on in the plant, which we just include with the actuator signal because of laziness, right? We just add it directly to the actuator signal. And in fact, we say process noise. In fact, it can be all of these things. So this is a sort of a catch-all signal to indicate saturation in the actuator signal, noise in the actuator signal, or process noise itself. Clearly, however, this is an external input, something we can't control. We don't want noise, we don't want saturation, we don't want process noise. So this is something we can't control. If we did, we'd just get rid of it. So that's an exogenous input. Right, so if we're keeping track here, right, we can write our Z regulated outputs, can write our sensed outputs, we can write our disturbances, and we can write our actuator inputs. So let's now we've gotten to back to the system, and so we can sort of tidy up. We're going to call this signal Q, and generally it's a good idea to label all your signals when you're doing these block diagram algebras. And the output we're going to label as R. All right. So let's see, what do we got here? Well, in Y, of course, Y is just Y. There's only one sensed output. For our regulated outputs, we have two. We've got this YP, the output of the process. We've got our U, so that goes there. Likewise, over here under our exogenous inputs, we have process noise, and we've got sensor noise. Inputs from the controller, right? Just U, right? We just label that U. Right. So those are our 6 signals, 2 and 2. 2 inputs, 2 outputs. Right, and so now we've sort of labeled everything. And now we have to write this in the 2 input-output framework, right? So we have to find this plant, right? This aggregate plant, which is, of course, not the same as, right, the nominal plant. So the feedback plant, if you will. So here's our Z's, here's our Y's, here's our inputs W, here's our inputs U. So how do we write this down, right? So basically it's a spaghetti diagram, right? So we have a nominal process here in the middle, right? And so we just we connect these signals through wires. And so what do we have here? Well, let's follow our signals the same way we followed them over here. So the input to the plant, right, Q, well, what is that? Well, it's a combination of this wire from the process noise added to the input from our controller, right? So there's those 2 equations here. So we can actually write just down the equation for that. Q equals W1 plus U. Next, what do we got? Well, we have the output from the plant, which we call R. You can write that R equals P naught Q. There's an equation for that. Next, well, what do we have here? We got this output. Well, where does that output go? Well, as we indicated here, one branch of that goes to a regulated output, which is YP. So that's going to give us equation for Z1. The other branch is something which is corrupted by sensor noise, and so we bring in our now exogenous input there, corrupt our sensor noise, and send that to the controller, right? So there's another equation, the R plus this corruption. And finally, we have the second regulated output, which is just the input. And so we have a wire, we branch off this input, and we wire it directly over here to the exogenous output. So now we have 5 equations here, and this set of equations allows us to then write down the system representation of the larger plant P, the system plant. Okay. So let's write down those equations. I guess actually I lost them from the previous slide, so we can just write them down. Well, Z1 is the output from the plant, which is P naught, which acts on W1 plus U. We have the second exogenous input, Z2, which is just U. We have the output from the sensed output, which is the output from the plant, which is P naught W1 plus U, corrupted by sensor noise, which is W2. Okay. And so we can write down these 3 equations, or we can write down this aggregate plant, right, by just representing these equations, just writing them down. So we expand them out, P naught W1 plus P naught U. So we have Z1 equals P naught W1 plus P naught U. So we have the first equation. The second equation, right, is just Z2 equals U. So just Z2 equals identity times U, right? So we have the second equation. And then the third equation, Y equals P naught W1 plus P naught U plus W2. So P naught W1 plus identity times W2, and then P naught times U, right? So we have these 3 equations, and again, right, because the systems are in algebra, we can just write these down directly as our larger system representation, which we have right here. Now again, I mentioned in a previous slide that this concatenation of systems does not necessarily translate to concatenation of the state space representations. So here we have our 4 systems, right? By the way, this is P21, this is P22, this is P12, and this is P11. Right, so there's 4 subsystems. So how do we write a state space representation of this? Well, that's actually a little bit complicated. You have to actually write down the equations and figure out what's going on. So I don't do that in the slide, but since I did it in the previous iteration of this recording, I guess I should do it again. Right, so how do we do that? Well, so if we go back to these equations, right, write them down again. Right, we have Z naught, right, Z1 is P1 W1 plus P naught U, or P naught, sorry. Z2 is U, Y equals P naught W1 plus W2 plus P naught U. Right, so what we're going to do then is take these signals, and so this is Z1, this is Z2, this is Y, right? This corresponds to W1, W2, U, and we write down the state space representation of the output of this signal. So we've got P naught W1 plus U right here, and P naught W1 plus U plus W2. Okay. So we write down an expression for this, the output of this thing here. So what is that? Well, what's the state space representation of P? Right. Well, it's x dot say equals AX plus B, and then the input to that system is W1 plus U. Right. And the output of that system, y equals Cx. And then we have the D, right, W1 plus U. And so now we can write this. This is signal Y. This is signal Y. And so we can write down a state space representation. Well, here's the expression for x dot, right? That's equal to A times X plus B times W1 plus B times U. Right? So the output of the system, right, is just equal to this this Y. All right. So the first output is Cx plus dW plus du, right there. So that's the first equation. Z2, right? Well, that's just U, so we have a direct feed-through term here. The third equation, right, is the signal Y plus W2. So it's the same as the first equation here, right? Cx plus D W1 W2, so Cx plus dW1 du, and then we add W to it, and so that comes in right there. So again, right, it's the same sort of signal decomposition, but now we have an extra constraint that we have to add that x dot in there as well. So that's the challenge for writing down the state space representation of this larger system P. And so how you get from here to here is not straightforward, right? You have to write down these signals and write down what they're equal to. For the tracking problem, that's actually a homework problem. Of course, if these were transfer functions, we could just write down the aggregate transfer function, but then there'd be all sorts of repeated poles, and that wouldn't actually help us that much. So another example, before we get to the tracking problem, is a system diagnostics thing. And this is purely a spaghetti diagram rewiring, right? So in this case, we've got, so what is actually an extra exogenous disturbance. So here we've already written down our 2 inputs, 2 outputs. But in this case, we want to say, give a signal to the controller to say, change how the system operates, or to nudge the controller in one direction or another. But it's not part of the automatic control system. So this is like the supervisor is telling the control system to change operating procedures. And again, like in the tracking framework, it's not something that we can control. And likewise, we have some outputs from the controller, maybe representing how strong our control signal is, if we're about to break the system, how well we're tracking the output, something like that, which is something we want to minimize. So we want to minimize this disturbance to the controller, some outputs from the controller, the supervisor. So this is a exogenous input, and this is a regulated output. Right. So we can just take this two signal representation, but now we have an additional signal here, U command, and actually it should be up here, Z diagnostic. Right. So we've inflated our Z's slightly, and we've inflated our W's slightly. Right. So the only difference between this augmented system and now the inflated number of signals, right, is that we've added a couple things, right? Y here and U here. So okay, let's put this in closed loop. So the only new signals we have are this U diagnostic, right? So what's the effect of that? Well, obviously that U doesn't go into the plant at all, right? So that it bypasses the plant entirely and goes directly, gets shuffled off directly to a regulated output. Similarly, this extra input to the controller doesn't go through the system at all, right? It goes directly from these commands, gets shuffled off directly to something that the controller can see, right? And so the equations for this are relatively simple. They're the original equations, just with some identity matrices thrown in. So I won't actually go through the aggregate here, because this case is actually relatively rare. You're unlikely to see it very often. More interesting for most people is the tracking control problem. So this is the cruise control, where the user sets their desired speed, and then the output of the plant should track that desired speed. So think of a step input, right? You don't want the output of a step input to be 0, as you probably had in homework too. It didn't go to 0, but it didn't go to your step input. The purpose of the tracking control problem is to make sure the output from a step input, for example, is in fact the step. It's 1, right? So in this case, it's more or less the same. I mean, this is more or less the regulator framework we have down here, right? So this is more or less the same. The big difference, of course, is what we choose to be our regulated output. Okay? So in this case, we don't want the output of the plant to be 0, right? If we want to call this, what are we calling this, Q or something? We don't want that to be 0. Instead, we have a desired signal, a reference signal, and we want the difference between the output from the plant and that reference plant signal to be 0. So this error, which we define as the difference between the output of the plant, or I think before we called this YP, and the reference, right? We want that to go to 0. Right, so this is going to be a regulated output. So if we start keeping track of these things, right? We've got Z, we've got Y. First, Z is going to be this error signal. Right? And then the inputs here, I'll just for completeness, start keeping track of these things. Put those right there. All right, so there's that regulated output. So as before, we assume that we can measure. We have a sensor which measures the output from the plant, right? But of course, it's distorted by sensor noise as before. And again, right, the sensor noise is not something we can control, right? So this is a exogenous input. Again. And so to keep track of these things, right, we're going to put that sensor noise in the exogenous input. Let's see, did I make it 1 or 2? No, we're going to make it number 2, so I won't get ahead of myself. Actually, it's 3, right? So number 3. We would put it down here. All right. So okay, so then that gets added to Q, or the output from the plant, and that's the sensed output, right? So Y is Q plus W3. That gets shuffled off to the controller here, right? Now the controller, right, can measure the sensed output. But now we have to think a bit about how this reference input is handled. Right? So as before, right, the reference input is not something you can control. You can't control whether people want to go to 60 or 70 miles per hour, although maybe that's the purpose of speed limits. But in the control framework, that's not something you can control. So we're going to have, it's an input, but it's not something you can control. So by definition, it has to be exogenous, right? It has to be an exogenous input. All right. So that's the first thing. So that's going to get shuffled in. Now, what do we do with that? Well, first of all, we note that 99% of the time you can measure what the exogenous input is, right? In a cruise control system, right, the controller can measure what, presumably, you desire the speed to be, right? And so typically we shuffle. You don't have to be able to do this, but typically we are allowed to measure the reference input, right? And so we're going to include that in the inputs to the controller, the sensed inputs. So we're going to include R there as well. So that's interesting because this reference is now not only an input, but it's also an output, right? So it's an input, but it's also gets wired directly to an output of the system. So we're going to have to take that into account in the spaghetti diagram. But it also, of course, gets shuffled off here, and right, you measure the difference between where the plant is and the and where the reference is, and that forms your output error. So it's an exogenous input. It gets mapped directly to a sensed output, but it also gets shuffled off over here to the error. So there's going to be lots of wires going over there. Then, of course, as in the regulator case, we have a control signal, an actuator input, right? And that is U. That's what we're allowed to manipulate. So this is here, U. And so we'll write down U there without changing the letter. As in the regulator framework, we get sensor noise, we get actuator noise, we get actuator saturation, we get process noise, all coming in through this exogenous disturbance here. Oh, sorry, wrong color. Oh, actually, this is the wrong color. No, oh, actually, no, sorry, that's the right color. There, that's also an exogenous input. And those get added together and shuffled off to the plant, which then closes the loop. All right. So we've got, see here, our exogenous inputs. We've got sensor noise, process noise. And, of course, we've got this, the reference signal, right? So if it's, this is an exogenous input, and exogenous inputs. We have 3 exogenous inputs, 1 actuated input. So technically our P, when we have it, will map those 4 W signals in, but of course, so it's a 2-input framework, but input 1, of course, is a concatenation of 3 separate signals, which of course may individually be vectors themselves. And it maps those to the Z and the Y. The first Z is, of course, the regulated output. Oh, sorry. That's my bad. This is the actuator input there. And then, of course, it gets mapped directly to a regulated output where we're trying to minimize the effect of actuator. So again, we can just fill out the second one here, U. So for our output, we have 2 signals, each of which is has 2 signals in it. So actually 4 outputs. 4 outputs, 4 inputs, but the size of these individual aggregate signals is different. So now we can form our spaghetti diagram, right? So we have these equations that for what are our inputs and our outputs. So remember, this is W, 3 exogenous inputs, 1 actuator input, 2 regulated outputs, and 2 sensed outputs here. So this is R and YP plus eta sensor. So let's we can just write down the equations for these, right? So here's our input, right? Just follow the spaghetti diagram, right? As before, this gets branched. One branch goes to, right, the regulated output over here. The other branch here gets added to the process noise, and that forms the input to the system, right? So the input to the system here and here, but we were calling that R before, but R is already taken, so we have to call it something else. Let's call it P maybe, right? That gets acted on by the plant, and so the output of the plant then, which we can call Q, for example, or Y maybe, that'd be better, except Y is already taken, so we can't use that. The output for the plant, right? Well, one version of it gets different from the reference input, right? So this forms the error signal. And that is our regulated output, right? So that's regulated output 1 there. And of course, we already had the other regulated output right there. Now for our sensed outputs, right? Well, as I said, one sensor signal we have available to us is the reference signal itself. So that's the first sensor. And then the other one is the output of the plant, but now added to this sensor noise. So the sensor noise comes in, gets added to the output of the plant, and that's what we can sense. So it's this sensor noise plus the output of the plant, which is actually all of this, which is Q. Right. So, right, we can now write down our equations, right, for our aggregate overall plant in the feedback interconnection. The first of which, so signal Z1, Z2, Y1, Y2, and then acting on W1, W2, W3, and U. So we just take these equations. Z1, right, is, this is R, remember, right, is just the, well, maybe I should write it down. W1 minus P0, W2, remember this is W2, minus P0 U, right, by linearity of the system. This one is obvious, don't need to write it down. This one is W1, and this one, right, is W3 plus P0, W2 as before, plus P0 U, right. So now we write down these equations in our system framework. Here's our first equation. Z1 is W1, just identity, minus P0 W2, there's W2, minus P0 U, there's U. Second equation is just Z2 equals U, so just Z2 equals U. Third equation is just Y1 equals W, so just identity there. And the last equation is W2 is W3, there's identity there, plus P0 W2, P0 W2, plus P0 U, P0 U, right? So just looking at these equations, the wiring diagram, we can write down the feedback control formulation of the system. Now, emphasize, of course, that, right, the state space representation you have to work out on your own, and that actually, for the tracking problem, that's a homework assignment, so I'm not going to give you the answer to that right now. But there's, it's not just the concatenation in the same way that we see here, right? So you're going to have to write down these equations for x dot. Then we have 4 signals here, Z1, Z2, Y1, Y2, and then X, we have some additional signals here, W1, W2, W3, and U, right? So this will be 5 matrices here, 5 matrices here, and 4 by 4 matrices there. So you have to figure out this. Do this for homework. So just write down, as we did for the regulator problem, what these equations are, and just write it in the state space form. Right. So now we've shown, right, how to take sort of standard control problems and write them in this 2 input, 2 output representation. So to construct this matrix, the system matrix, or system operator, or system representation, P, which has some relationship to maybe a nominal system, or we don't know where get it, and maybe many of them are just identity matrices and wiring parts. But the first step is to construct the system representation of P. Right? And I think I just went over of P. Right? And particularly, right, you've got to find the state space representation before we move on in state space. And I haven't shown you, there's no general formulation for how to do that. In the next part, part B of this lecture, which I'll hopefully not have to record twice, we will now include the state space representation of K, and armed with this sort of general representation, right? We have A, B1, B2, C1, C2, D11, D12, right? This 6 matrix representation of the nominal system. We'll close the loop and find out what the closed loop system representation is so that we can then optimize it, right? So again, right, I emphasize that the whole point of this first part of the lecture is to get from whatever control problem you happen to have to this 4 system or 6 matrix, or sorry, not 6, 9 matrix representation of the plant that you're trying to control. Right, so that's the first step. Get this 9 matrix representation of the system. And usually when you're solving control problems, you just sort of start with that and don't have to formulate it. But if you actually have a particular problem you're formulating, then constructing this 9 matrix representation is your first step. Once you're done with that, right, these are variables. So this is the data to the optimization problem, and these are your variables. And in the next part of this lecture, we'll talk about how to then take these and formulate the control problem in isolation. So I'll stop now and come back to that when I have more time.